Okay, so last class we talked about information complexity, distributional complexity, and kind of the general philosophy between direct product theorems, right? So here in direct product theorems, these occur in very different fields, but always the concept is the same. They occur in communication complexity, in circuit complexity, in cryptography, and many other places. So here you're mainly trying to understand if solving n copies of a problem is should be n times as expensive as solving solving a single copy. There are some very important exceptions to this, but there are many cases where we think it is true, we know it is true. There are also many cases where we think it is true, but we don't know it is true. Okay. Some famous exceptions to this sort of direct product theorems are computing n sort of vector-vector multiplications. Okay, that's like matrix-matrix multiplication. You can do much faster than doing them all separately. Another example is FFT and so on. Okay, so today we're going to talk about this proof for communication complexity. We'll focus on disjointness lower bound, but as I said, one reason we're doing this is that this proof technique is extremely versatile and also gives us the best direct product theorems that we know. Okay? In fact, the actual protocol that we'll see is very close to the protocol that you need for the direct product theorem. All right? Okay. So before going on, one announcement is that remember that exam 2 will be out on February 27th at 6 p.m. Okay, you have 48 hours afterward. Yeah. So it's going to cover until lecture today. So basically, we did not have sensitivity conjecture last time, right? So it was only the first 5 lectures, more or less, okay, or maybe 6. So so topics will be I'm right. Sensitivity wasn't covered, right? Yeah. Yes. Okay. Sensitivity conjecture, sunflower, and information complex. Okay. And the last exam will cover whatever is going to happen in the next 5 lectures. All right. Any questions about the exam? The same format, it'll be uploaded on Gradescope, and you'll have 48 hours. You can look up whatever you want, but you have to do it by yourself. Okay. All right. So, all right. Okay. So let's get started. Let me do a quick recap. Last time I talked about many things, but if you just want to focus on the information complexity lower bound of disjointness, it's a bit cleaner. Maybe I should have stressed that last time too. If you're not interested in the fully general picture, the motivation kind of for the argument is as follows, right? So we said, imagine there is a protocol for computing disjointness. Okay, and what does it mean for it to compute disjointness? It means that for all x comma y, probability over the randomness in pi. Okay, so here probability pi means that I'm taking the probability over the randomness in pi. X and y are arbitrary inputs. Equals disjointness of x comma y is greater than or equal to 0.9. Okay, and we're going to take a look at such protocols and then argue that these protocols must have a lot of information, a lot of mutual information between x and y, okay, in our sense of definition of protocol complexity, okay? But we're going to measure the information hidden in the protocol with respect to a specific distribution. Okay. So, uh, so what do we know about this setting? One, for any distribution, let me call it mu. Right? So this we always know that the information cost of the protocol with respect to this distribution is at most the length of time. Okay. And now we're going to do two things. Choose mu to be sigma to the n. Okay. So we had the specific distribution which we are going to use for our measurement of information complexity. Okay. And now what we're going to show, and this is where the information complexity really shines, is to say that for all protocols pi, we must have okay, so this is kind of the really key theorem, right? We're going to say that you started with a protocol which is accurate, okay? And using that, we're going to get another protocol whose information complexity is small, all right? And it actually computes the NAND function, right? Okay. So you're going to use a protocol for disjointness, which is a function on n bits. Seems silly, right? So I have a function on n bits or a protocol that is solving a problem on n bits, but I'm going to use that to design a protocol for computing the single bit NAND function, right? Some kind of reverse, you can think of it as a contrapositive of a direct product theorem, right? And in fact, many proofs go this way. They're like constructive in some nature. You assume I have a very good protocol for solving this n-bit instance, and I'm going to use that to get an even better protocol for the 1-bit instance. Okay, we're saying it scales down linearly 1 over n, and then the second part is to show that is less than some constant. Okay, and this constant actually we know is like 0.48 or something, right? Okay, so this is all good. One thing I realized yesterday was that I made a small mistake in the definition of information complexity. Yeah, go ahead. Yeah, question.
It's like, so in definition one, is the opposite inequality.
The opposite one is not immediate. Okay, so you can prove it. It is kind of true. The only way it's not true, it's not immediate is, okay, so what would you do, right? That's a very good question. So let's say I tell you that, I have a protocol for computing NAND with it's very, very good, then how would you use it? You would just do it for single bits. Okay. And then you can use it for, once you know it for single bits, you can just solve the full thing just because disjointness is just an AND of NANDs. Okay. The only caveat is that the guarantee for NAND is 0.1. So you have to make sure that the error probability has been driven down so that you actually get 1 over n. Okay. So apart from that, it works as is. Even with that, you can do some bootstrapping and some kind of amplification to get some rough equivalent. Okay. All right. So the one correction I want to make is that remember how we define the information complexity of a function, right? Maybe let me just go back to the definition and I'll tell you what the mistake is. Okay. So the mistake here is that this is not a min, that's an inf. Okay. So there are distributions where the minimum is not achieved. Like basically to get the ideal cost even for the NAND function, the protocol length has to keep on increasing if you want to get the absolute constant. Okay, and like, I think this part is fine, but here's where it's an inf and not a min. Okay. All right. Okay. So let's focus on this one, the first part, which is I would say the heart of the proof. We're trying to say that the information complexity of the single bit NAND function with respect to the distribution sigma is at most 1 over n times the cost for disjointness with sigma to the n. Okay. All right. So how do we prove such a thing? And as I said, the proof is going to be constructive, and it's a theme that shows up in many direct product theorems as well. Okay. So our goal is to say that okay. I might have changed this order of sigma and 0.1, but you know what they are. One is the distribution, one is the number. Okay. All right. So how do we show such a thing? As I said, we're going to be constructive, meaning what we have is a protocol, pi star. Let me call it pi star, just to kind of emphasize that we are given some protocol. Someone told you there exists this very nice protocol, right? For computing disjointness. Okay. So meaning for all x comma y, okay, we have this, and we want to use pi star to get a protocol for a single bit NAND, but whose information complexity is smaller. So let's say pi star is very good. Maybe its information complexity is like root n or n over log n or something like that. Okay, something that we don't believe exists, but we want to use it somewhere. So how can I use pi star to get a protocol for NAND? Any guesses? Like, okay, so what am I trying to do now? What is the computational problem I'm trying to solve? It's kind of a seemingly silly question, but it's not really. I want a protocol pi. Here A is just 0, 1. B is a single bit. Okay. and Alice and Bob want to communicate and compute NAND of A comma B. Of course, they can just send a single, Alice can just send A across and you'd be done, right? But that's not the point. We want to say that somehow if there exists a very good pi star, I can actually do even better than sending a single bit across, okay? And this is where information complexity is important, right? If you think of communication complexity, it is discrete. You can't say you're sending less than a bit. But information complexity can allow us to make such arguments or calculations, okay? And there are other ways to do it, but at the very least, syntactically, you cannot do it in such simplicity when you deal with communication. Okay. So, as I said, think as a toy case that IC of pi star comma sigma to the n is something like, maybe root n, or let's say 0.001 times. Okay. So now what are we trying to say? We want to use this pi star, which has such small information complexity, to get a protocol for NAND whose cost is basically 0.001. Again, that's how we are going to get a contribution. If it's sending a single bit, of course, that's 1 bit. But we're looking for something way more efficient than even sending a single bit in terms of information. Okay? That's why it's a little bit counterintuitive, but you'll see we can do it. Okay. So how can I use this protocol, pi star? Maybe let me do one more change in notation so that it sticks. Like there's a pi star n, meaning the protocol is on n bits. Okay. I don't want that to be confused with pi. All right. Any suggestions? So what can I do to use pi star somehow? Let's brainstorm a little bit and then we'll find that there is a very clever solution. But let's first try some things. How can I use pi star to get a protocol for NAND? Think of the simplest thing to do. Okay. Well, okay. Yeah, let's try that. Yeah. So, okay, here's my candidate one. And in some sense, I just want to compute NAND of A comma B, right? But what is NAND? What is disjointness? Disjointness of two inputs x comma y is and I equals 1 through n of the individual NANDs. Okay. So for example, I can just say that here's my protocol. I'm going to set x to be A and all zeros, and y to be B and all zeros. Okay. So now clearly disjointness of x comma y equals NAND of AB. Right? Because in every other bit, NAND of 0 comma 0 is 1. So when I take the AND, only the first bit is determining the output. So if I compute the disjointness, if I run the disjointness protocol on this large inputs x and y, I get the single bit answer. Okay. So we run pi n star of x comma y to get AB. Okay. Does this bias anything in terms of the cost? Right. So, based on this, maybe the protocol says you exchange a lot of bits, pi n star, something, 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 And then you end up with an AND of AB equals disjointness of X1. Okay. This seems like, it does compute the function, but in terms of information cost, do we learn anything? What do you think? First of all, one big issue is that the only thing we know about pi n star is that its information cost with respect to the specific distribution sigma to the n is small, right? So even if we're not even making good use of the hypothesis, right? This is our hypothesis, that its information cost is small with respect to one specific distribution, right? Remember, the distribution choice actually matters. If you use different distributions, the information cost can fluctuate a lot, okay? So it's with respect to sigma to the n that it is small, but here there's no way to even bring in that hypothesis, at least immediately, because you have all zeros here. Okay. And also it seems silly that you would just plug in zeros and magically gain some. What if my protocol just exchange the first bit as it is? Pi n star says exchange the first bit. That's only one bit of information, right? Whereas we have our budget is like 0.001 times n. So I can definitely, pi n star could definitely be doing that. And if it's doing that, you learn, the information cost will be very high for NAND. Okay, so you're not getting a very good protocol for NAND. Okay, so how can I potentially fix this? There are two issues, as we said. One, not using okay, so we need to address both of these issues. How about first one? Any suggestions on how to fix that? How can we bring sigma to the n into the picture? And recall, what was sigma? Sigma is a distribution where 0, 0 happens with probability 1/3, 1, 0 happens with probability 1/3, 0, 1 happens with probability 1/3. Okay, right? So this is a distribution on sigma, right? Now, what do you notice about all of these three inputs? What's the NAND of them? NAND is 1, right? NAND is 1, okay? So what's another way? What's a way to bring sigma into the picture? Even if I want to use kind of the same template. Any suggestions? So what did we do here, right? So we used zeros because the NAND was 1. Okay, but it kind of was useful in that it gave us the functional property that we want. But the distribution on x and y was not what we wanted, right? We want the distribution to be sigma to the n because that's our hypothesis. We want to bring that into the picture. So how can I get the distribution to be sigma to the n? Any suggestions? Exactly. Right? So what we're going to do is the following. So instead of them picking A and B like this, right? So what we would ideally like to do is the following. Again, there's some issues with this. We'll fix it in a second, but let's just say this is what happens. Maybe Alice samples, we want to sample x2, y2, x3, y3, so on, x and y. Okay. So here's the sort of new protocol that we have in mind. Okay, so each xi, yi is sampled independently from sigma, right? So x2, y2 is going to be exactly one of these three options, 0, 0, 1, 0, or 0, 1, each with probability 1. x3, y3 also is going to be the same thing, independent, and so on and so forth. Okay, so after this, the idea is to now run pi n star on x comma y. Right, this is x, this is y. Why is this still a meaningful thing to do? Well, we do have this equality, right? So this still holds. The fact that disjointness of x comma y is still just the NAND of a comma. Okay, this condition, which is important for us, still holds. Okay, and the marginal distribution of x and y is sigma to the n, which is at least helpful in bringing the hypothesis back into play, right? So we have this, and then we have C, x comma y is distributed as sigma t, right? Because A comma B also came independently from sigma, and the remaining things are also sampled from sigma. So what we have is actually product distribution sigma to B. Okay. Any questions about this? Yeah.
Is B hold the type of?
That's a deterministic statement. The function output, this is a deterministic statement. Okay. So, disjointness of x comma y equals NAND of a comma b. That's a deterministic statement, right? Why? Because, NAND of all of these things is just 1. And disjointness is the AND. So it only picks up the first one. Okay. So this statement is deterministic. The marginals are what we want them to be. Okay. But there are two issues. So what's the first issue? That's our assumption, right? Because we are interested in understanding, we are interested in showing this. Right, so we're trying to understand the information cost of the protocol, or get a protocol whose information cost is small when measured against sigma. Right? It's a good question. Okay, so let's go back. So our goal, find a protocol for NAND, let's say pi, such that okay. So we are trying to show that, in fact, by small, we want it to be 1 over n of IC of pi star n comma sigma to n, right? But we are measuring the cost also with respect to sigma. So A and B are sampled according to sigma. Okay, so you can assume they are sampled according to sigma. So we have the marginals to be right, but there are still two issues. In some sense, okay, we already identified one of them, so this got fixed. Okay, and how about the second question? We did not fix that, right? If my protocol pi n star exchange the first bit, then the information cost will be very high. There's no escaping that. The protocol completely gave away A, So it is going to be some constant, in fact, the maximum possible thing. Not 1 because it doesn't have 1 entropy, but like h of 2/3 or something. Right? So how do you fix that? Any suggestions? Like somehow, why are we focusing just on the first bit? Right? So how can I get around that? Is there something special about first bit in this construction? Choose a random I, right? Okay. So that's going to be our attempt number 3. Because there's nothing special about 1. But if you know that our simulation is only going to use 1, we might be in trouble because, maybe the protocol exchanged too much information about the first bit. All right. So now what Alice and Bob are going to do is the following. So 1, pick a random index I. Okay. We can assume I is like public randomness. It just goes into what you condition on in the information cost, right? So let's say using public randomness. Or you can even exchange it because it is small enough that it gets rounded into little O((n) errors. Okay. And then sample x1, y1, x2, y2. Okay. So this means somehow we are saying, okay, let's put x1 here, x2 here, all the way to xi minus 1. And then in this special cell, we are going to have 8. Right? In the same here, y1, y2, yi minus 1. In this special cell, which is aligned, we are going to put b. Right? So the kind of intuition behind planting the random 1 is some kind of averaging argument, right? So imagine that the total cost of the protocol, it's helpful to have this intuition, but sometimes it is false when you work it out. So it's only intuition, okay? It's not proof yet. So if the total cost, let's say, is like 0.001 times 10, okay? So the heuristic calculation, okay? We know that IC of x comma y given pi is again, this 0.001n is whatever arbitrary, right? So we just that's placeholder for our intuition. Okay. So the way we define information complexity, the information complexity term has 2 terms, right? Let me see if I ever expanded that out. I guess no, but it's okay. Okay. So this is the mutual information between x and y conditioned on pi and star plus, oops, sorry, the other way around. Okay, this is what we have. And this is just the definition of the information cost, and then we have some upper bound that we assume. So the intuition roughly is that let's focus on this one term. Okay. This is basically x1 through xn and pi n star of y. Right. So if we use chain rule, then there will be n terms here. Okay. So the heuristic calculation is that I have n terms. Together, they're adding up to 0.001 n. So if I pick a random index I, this should be about 1 over n times the total. Right? So I can write this as by the chain rule, summation I equals 1 through n, I of xi, pi n star, x1 through xi minus 1, comma 1. Right? So if I pick a random index I, then this value is basically 1 over n times this, right? The expected, in some sense, cost. Okay, so that's the heuristic calculation. Okay, so if I pick a random index I, at least this much is true. But of course, there's a difference in that you are conditioning on a lot more. There's yi as well, the whole of y. So we don't know how to play that out. Okay. But at least, does it make intuitive sense as to why planting it at a random location could be useful? It's because of the chain rule, to put it at a random location, we expect the contribution of each individual term to be about 1 over n times the total contribution. Okay, and that's what we are shooting for, right? We want to say that this cost is at most 1 over n. Right? Okay, so it seems to be following along the things that we want, right? So we almost have this 1 over n here, and this is like the expected cost that we would see when you pick a random index I. But there's one big issue in this protocol. Right? Can you tell me the issue? So if you think about it, so this is our full protocol pi for NAND, right? So pi is not just this bit, not just this, the whole thing. I'm given single bit A, Bob gets a single bit B, and we're running this protocol. We pick a random index, we do the sampling, then we do this, and then so on. Okay. So my claim is that there's a big issue with this protocol that we pushed under the rug very conveniently. What is that issue? Well, the issue is we basically are debating whether the chicken came first or the egg came first. Right? What do I mean? There's a sample that we have to do, right? We have to sample this x1, y1, x2, y2 according to sigma, right? But how do you do the sampling without communicating? Because these are not independent things. Sigma has a joint distribution between xi and yi. Right? I just said, okay, sample, but I cannot do the sampling, or at least I don't know how to do it without communicating. And if I'm communicating to do the sampling, then that might completely kill the cost of the protocol anyway. Right? If I have to send n bits across just for the sampling part, then that n is going to dominate whatever savings you have for pi and stuff. And it almost seemed like we had a very good simulation, but there's this issue that, this sampling is not like immediate. Okay. Do you have a question or?
So if the randomness is like public, would this be a problem? Or this is very private randomness?
That's a good question. We can say, okay, maybe they'll use public randomness. But the point is, if you try and do that, the issue is that somehow then there is no hidden information. If it's public randomness, Bob also knows xi and Alice also knows yi. Then the mutual information will be 0. What you learn will be very small, and in fact, it won't be useful at all, right? So this equation would not hold then. I mean, this equation would hold, but this would have nothing to do with all of these terms would be 0. Just because, everyone knows what xi and yi is, right? So in the original thing, they had some very clever, nice solutions for this, a bit more intricate solutions. And this is not just a standalone problem. There are all these techniques called correlated sampling. This shows up in settings where I want to sample from some joint distribution, but how do you do this in a way which minimizes the amount of communication? You have to solve another communication problem. You have to come up with a very clever way to sample. Okay. But instead of that, we are going to pull a rabbit out of the hat and look at this very clever protocol due to Braverman and Rao from 2010. Okay. So their simulation or their way to use pi n star is as follows. And you'll see it's fairly generic, actually. You can use it for more general direct product theorems. And in fact, I think that's the main point. It's one of the salient features. Okay. Right. So what is my new protocol going to be? It's going to be somewhat similar, right? Except with some very clever twist. So we'll have these steps as before. We have 4 steps here, right? Except the sampling part will be a little bit more nuanced. How so? So let me erase this and talk about the sampling thing fully. Right? So the first step is going to be the same. Pick a random index I uniformly from 1 through n. Okay. So if you think of this as the public randomness cloud that both of them see. Okay, so this is the public randomness. Then we're saying the index I is here. They could also exchange it, but just assume it's known. Okay. And just as before, their idea is to plant A and B here. Like, set xi equals A, yi equals B. So set xi equals A, yi equals B. Right? But what changes is how we sample. As I said, the issue is that both of them need to agree on this conditional sample, but they're joint, they're correlated. So like, for instance, if xi is 1, the other one must be 0. But how do you do the sampling without communicating? Okay. And they said, it's not that we need them not to communicate, but what we need is somehow the information to play very nicely with the chain rule. The protocol should play very nicely with the chain rule. Okay. So here's what they suggested. Let me draw a different picture, actually. Maybe let me use some nice color coding. Why not? If they are aligned horizontally, just think of them as the same I. Okay. All right. So far, what did we get? This is xi equals A, and this is yi equals B. Okay, that's the only thing that we have. Bad choice of the color, but hopefully you can still see it. Okay. And here comes the twist. They said, okay, so Alice is going to sample x1, x2, all the way up to xi minus 1 from the cloud. Let me put bars there just so, just to separate the things for notation, okay, to emphasize what's different, right? And they're not going to sample xi plus 1 up to xn. Okay, so earlier they were sampling x1 and everything together, right? There's some asymmetry we are introducing. What is this asymmetry? And Bob is going to do yi plus 1 bar up to yn. Okay. So this cute things a little bit. Oh wow, these colors are terrible. All right, let me change the coloring scheme. Hold on. This projector is awful. Okay, that's better. And let's do red. Okay, good. So what did we do? So we said this is x1 bar, x2 bar up to xi minus 1 bar. Bob chooses yi plus 1 bar all the way up to 1. Okay. So what we are saying is, okay, I'm going to sample this x1 through xi1 bar, xi minus 1 bar, yi1 bar to yn bar. Okay, two distinct segments, right? What distribution should we sample this from? Okay. So the idea is the following. For j less than or equal to I, less than I, use public randomness to sample for each index. We're going to sample x bar j. Under what distribution? What distribution should we sample from? Take a guess. You know, what do we want, right? We want this marginal to be consistent with sigma to the n. So the distribution on x1 bar should be, where did sigma go? Sigma is this, right? So what should the distribution on x1 bar would be? 0 with 2/3, 1 with 1/3, right? You know, if I sample from sigma, the marginal is exactly that. Okay. So we'll say sample xj bar with right. So this is the marginal of sigma on a single bit. Now, once you do this, what Bob does is this information is public, right? So Bob now knows x1 through xi minus 1 bar. So for each one, Bob samples conditionally from the y. Okay. So what does it mean? After this, Bob uses private randomness. Okay. So what does this mean? If xj bar equals 0, then the conditional distribution on y is uniform. There's 0 and 1, each occurs with probability half, right? So the goal is to have xj and yj have the same distribution as sigma. Now I sampled xj. So how should I sample yj? From the conditional distribution. Okay. But the point is Bob is using private randomness to do this. So we got the marginal consistency that we wanted, but there is still something unknown about the distribution, which was important. If everything was done publicly, there's really no information to be gained by running the protocol. But now, because Bob is using private randomness, Alice doesn't know the exact value of yj bar, at least with some probability. Okay. Then yj bar is uniformly random from 0, 1. Okay. On the other hand, if xj bar equals 1, the conditional distribution is just as a single point. Right? So there's only 1, 0. So Bob's output will be fixed. Bob's bit for this particular j will be fixed to be 0. Okay. So that's the cleverness. In some sense, they do this first, these green parts, which are randomly chosen. And then Bob fills out this portion by sampling conditionally. You know what? Actually, let me do something. Let me put y1, y2 without the bars to indicate that they are private randomness. Okay. And the same thing for Alice for the remaining things. Okay, so we kind of switch between who is doing the sampling first. Alice does all of these first using public randomness. Bob also knows this, so Bob now does the private randomness. And then Alice looks at the public randomness to sample these conditional. Okay, so they both get their own turn. So these are again private randomness. For j greater than I, use public randomness. To sample yj bar such that probability of yj bar equals 0 is 2/3. Equals 1/3. Okay. And all right. And then they run the final step after all of the sampling is run pi n on x and y. All right. So the point is now this whole protocol, what is being exchanged? You exchange the index I, and after that, only this communication from, actually even I is public randomness, right? So they're not exchanging anything apart from what pi n star is doing. Okay, they did the sampling with 0 communication. And at the same time, it's not as if everything is public. Both know everything, right? Alice doesn't know what y1 through yi minus 1 are. Bob doesn't know what xi plus 1 through xn are. Okay. Right. So this is a very clever sampling thing, which makes everything much, much nicer and neater. Yeah. So, it should show up, right? So basically what can happen if you put everything in there is that when you look at the mutual information, you have to condition on the public randomness. And once I condition on something which determines my input, I lost all the information. Right? So there is a trade-off, but somehow the trade-off here is such that I'm not conditioning on everything. There's still some uncertainty left that it'll make it work. Yeah, exactly. Right? Okay. So is the protocol clear? It's a very clever protocol, as I said, and there's some intuition for why we are doing it, right? So we can get at it step by step. We want to plant A comma B at a random location, but then we have to do this correlated sampling. How do we do that? We kind of get around that by saying we want to use public randomness, but still have some uncertainty. Okay, and that's where this comes in. Right? And before we start doing the main proof, we can deduce two simple things. Kind of simple in the sense they follow from the definition. X comma Y are distributed as sigma to the n, right? That's exactly what we're doing, right? A comma B is sampled according to sigma. So these coordinates are same and everything else is independent. So the marginal distribution or the joint distribution in X comma Y is exactly sigma to the n. Okay, that property, which was necessary because that was our hypothesis, is maintained. The next one, which is also kind of true, is that we have the functional equality that we wanted. Right? Other than A comma B in the ith position, everything else is the NAND is exactly 1. Right? So when you take the disjointness, it's completely determined by what's happening in A comma B. All right? Okay. The next thing that we are going to show, and which is, as I said, the key part is to say that right? So this whole 5-step thing, that's our big protocol pi. You do all of the sampling and also this running pi and star. That's our final protocol pi for NAND. Okay? And you want to argue that its information cost is very low. It's 1 over n times IC pi and star comes in. It is counterintuitive in some sense, right? Because if you think of pi, it's a huge protocol. You're running a protocol which was n bits. It started with a function with the protocol which was working on n bit strings. So pi and star could be very long, but the amount of information it carries is 1 over n times the length. Okay. So even though it's a very long protocol, its cost measured in terms of information is going to be very small. That's what we have to show. Okay. So let's take a 5-minute break. When we come back, we'll talk about this proof. So we started with single bits A and B. We designed this protocol, which kind of expanded the inputs in some way and ran this bigger protocol. But in the end, we're saying the information cost is actually very small. Okay. All right, let's take a 5-minute break and we'll do this proof after we come back. And I'd say in some sense, the hard work is already done with the sample. Now we have to follow with the chain rules a little bit carefully. The calculations now are a bit deterministic. We just have to work through them and make sure they check out. Okay. So what do you want to understand? We want to understand this IC of pi comma sigma, right? So to recall the definition, this means that we sampled A comma B. Okay. Right. So this is mutual information between A and protocol given B, right? So the first term corresponds to how much information did the protocol reveal about Alice's input A to Bob. Okay. And the same thing here. And I want to stress that in some sense, we started out with just single bits. Where Alice got A, Bob got B, and then we did all of this expansion in something else, right? The original inputs were just A and B, and then we created all of this imaginary stuff using x1 through xi bar and so on to solve the problem on A and B, single bits. Okay, so this is the main quantity we're interested in. So, so let's take what are all the main things. So we have the public randomness. So we have I x1 bar up to xi minus 1 bar, yi plus 1 bar up to yn bar, right? These are the public randomness bits. And then you have the protocol. Okay. So we can write down the mutual information between these two things is, let's take it one term at a time. Right, so let's focus on this term. So how much information did Bob learn about Alice's input given the transcript, right? And here transcript means you're also seeing the public stuff. Right, so these are all the ingredients. So you have to take this and the protocol into account. There's a public randomness, then there's a protocol exchange. So I put everything here. That's what pi is. Okay. All right. And okay. So the first thing I'm going to do now is a little bit well, okay, we'll see. We'll do many things, but I'm just writing it kind of in this way. It's the same thing. Okay, this is what we're measuring, right? So we have x1 through xi minus 1 bar, yi plus 1 bar to 1, right? And the first inequality we're going to use is that mutual information is monotone in the sense that, yeah, A is a single bit. Sorry, say it again.
You don't put like X and Y.
No, because, as I said, the problem that we're trying to solve is that Alice got a single bit as input, Bob got a single bit as input. And then our whole protocol pi was this thing. Right, so this is pi. Okay, so we had to calculate the mutual information between A and the protocol given B. Okay, so that's what we're doing. There are two parts to this transcript. One is the public randomness and the other is this. So we just put that here. So pi equals this thing. So I just put those ingredients together. Okay. And now this x bar and y bar also have these two components. And what I'm going to do is to use the fact that okay, so recall. I'm just saying that if I'm trying to measure the mutual information between A1 and A2, if I had some new stuff here, it's only going to increase the mutual information. It's not going to decrease. When you condition, it can change. But when I just give you more information, it can only increase the mutual information. All right? Okay. So I'm adding more stuff. So that's what we're going to do. Okay. So what does this mean? In particular, we get this is less than or equal to. And you'll see why this is helpful in a second. Okay. So this was not public random. This is only Bob knew, but I'm just adding that in. So to measure the mutual information, it should only increase it. Okay. So if you upper bound this quantity, then I'll also get an upper bound on the original thing. All right. So how do we do this? And we're going to do this in 2 steps. First, you know what? Let me just introduce some shorthand so that I don't carry these things everywhere. All right, so my shorthand is that I'm just calling this x bar less than or equal to I minus 1. Okay, so all bits less than or equal to I minus 1, and so on. So I'm going to use chain rule to break this up into 2 parts. So I have these random variables here, and then I have the protocol, the pi n star that I'm running. Okay, I'm going to separate these 2 terms out. All right. So this is chain rule, right? So I'm looking at the mutual information between A and these 2 groups of elements. There's the I, this part, and then there's the protocol. I just broke it up as in the first part plus the second part condition on the first part. Okay. So this is, recall chain rule for mutual information. So if I have I of A, A1, A2, or let's say okay. All right. So now tell me about the first part. What's the mutual information between A and these things? My claim is that we know exactly what it is. Let's go back to the picture. How we generated this, right? So we are looking at the mutual information between A and this, this, and this. Basically A and everything else condition on B. Okay. So what can you tell me about this mutual information? Do the other things depend on A at all? No, right? They're all sampled independently. I was sampled independently. X1 through Xi minus 1 bar were sampled independently. Y1 through Yi minus 1 were also sampled independently of A, right? You know, Bob never knew what A was, right? None of those things ever involved anything to do with A or B, okay? So A is independent of I and this independence holds for both A and B, in fact, right? So implies that this term is equal to a big zero, okay, plus something. And how about these three together? What are these three together? So I have y less than or equal to I minus 1. This part. I have y I plus 1 through yn. And then I also have b. So what are those three together? Y. Okay. So in some sense, we kind of simplified quite a bit, right? So we just have y. Okay. Any questions? All right. And now we'll use the definition of conditional mutual information. Right? So what is conditional mutual information? You look at the probability that that conditioning happens, and then you look at the mutual information, right? So if I just focus on this condition, I can write this as equal to the probability that I equals 1, which is 1 over n, right? So it's going to be 1 over n times the mutual information between I, phi n star, conditioned on, if it's 1, there's nothing that you're doing, right? So it's just y plus okay. Any questions? Right, I just use the definition of conditional mutual information only for I. So in particular, I can write this as summation I equals 1 through n minus 1, I All right. Now, what does this remind you of? What does this equation look like? Well, if I go back to our notation, we call this whole thing x, right? So in terms of x, what do we get? So this is just equivalent in slightly different notation to be, this is just xi. I have pi n star. I have x1 up to xi minus 1, and then I have 1. Right? I said the bars were just for me to distinguish between what is public and what is private, but now everything is already been conditioned. Okay. So what is this equal to? Let's see. We saw this. Right? It's the exact same thing. We're looking at the mutual information with one bit condition on everything in the prefix, right? So this equals 1 over n times the mutual information between x and pi n star conditioned on y. Okay? By chain rule. So remember, yes, so we are using the chain rule again. And this is good now because this x mutual information x and pi n star condition on y is a term that shows up in the information cost of pi n star. Right? Okay. So what did we learn from this? In summary, we build this crazy protocol, and the amount of information that Bob learned from this protocol was at most this quantity. And the same argument, just with X and with Alice and Bob's names interchanged, will give you okay. So this implies the information cost of the protocol with respect to sigma is the sum of these two things by definition, which is at most the sum of these two things which is exactly the information cost of pi n star with respect to sigma. Okay. So which is what we wanted. The information cost of the protocol that we designed is 1 over n times the cost of pi n star. Okay. So after we had this clever protocol, everything else was basically this, falling through the definitions and applying chain rule. Okay. Any questions? So we kind of proved this claim. So implies main claim. right? And if we go back to our outline, so what we just showed was that IC of, or let's say the information complexity of NAND with respect to sigma is at most the 1/times information complexity of disjointness with respect to the sigma to the n. Okay, so this is what we showed. Now there's a second thing that we need to show, which was this. This sounds very believable. Yeah, question? Right, so this is coming from conditioning on I, right? So how do we define condition-rich information? You look at the probability that I equals 1, and then you fix I equals to be 1, right? So that's one probability I equals 1 is 1/n. And it's 1, this is what you end up with, because x, there's no x there. And if it is 2, you end up with this guy. Okay, so we're expanding out the conditioning. I mean, technically, that's how it's also defined for y, xi minus 1 bar, and so on, but we don't have to open those up. We're just opening up the one for I. Okay. So we're almost done with the proof, but now we just have to understand this 1-bit thing. Okay, but this is also subtle. Like, in some sense, there should be some magic somewhere. Already there's some magic in terms of the chain rule, right? But remember, so far we never used the fact that the protocol is actually computing disjointness with accuracy 0.1. It's very generic. Okay, you had a protocol, you get the protocol again with similar guarantees. But we did not use this 0.9 or 0.1 anywhere. Okay, and it shows up in this last part. In some sense, what we showed is a reduction. Whatever you had for like disjointness, you get something similar for NAND. Now we have to show the limitation for NAND. Okay, and I'm not going to do the proof of this NAND thing completely. It's a little bit tedious. That's where you have to work through the numerical stuff a little bit. Okay, and it's a single bit problem. All right. Okay. So let's say I'll give a sketch for something like this, let's say. Yeah. You only need it to be non-zero. No. Remember, there's an inf. Okay. And there are problems where it is actually 0. Okay. The information cost can be 0. Okay. So it is subtle. But people have actually figured out the exact constant here. It's a very clever protocol, which is better than just sending A and B. There's some very nice protocol with some clocks and so on, which does very well. Okay. So even though it's a single bit thing, the ideal thing would have been to say, okay, it's compactness or something, and say it has been on 0, but it can be 0. You have to rule it out. I mean, in some sense, somewhere this error has to come into play, right? Otherwise, it is 0. Okay. All right. So how do we show this thing? And, it's more or less like working through the conditions and doing some arithmetic. Okay. But there's a very nice way to do it. You don't have to be too clever, but, let me just call this epsilon, because we'll keep multiplying them, right? So let's understand what this means, right? So suppose I had a protocol which is computing NAND, then the information cost of the protocol with respect to sigma, again, just using the definition, is A pi given B plus A B pi given A. Okay. Let's focus on the first term again. Right? And more or less, we're going to say that either this or the next term should be 0.002 or something. Okay. Now, how do I understand this? There's a, again, let's open up the definition of the condition. So what does it mean to condition? So this is equal to probability B equals 0 times the okay. What is probability B equals 0? Remember, A and B are sampled according to sigma, right? So what is this quantity? This is 2/3. You know, sigma, the marginals are biased. It's 0, 0, 0, 1, 1, 0. So probability that B equals 0 is 2/3. So this is 2/3 times okay plus 1/3 times
Recording in progress.
hello, hello, hello. Okay. Hello. Well, I hope it's recording, but I'm not sure. It's not recording? No, it's not getting the audio. It is recording. No, it is recording. It is recording. Yeah. All right. Well, let's hope it is working. Anyway, I'm going to wrap up soon. Okay. So what do you do now? So the second term, what can you tell me about the second term? If B equals 1, what's A? So remember the support is 0, 0, 0, 1, 1, 0. So if I tell you B equals 1, A is fixed. So what's the information there? There's no information. There's no uncertainty. Right? So this thing is equal to 0. Okay. So I just end up with this guy. All right. And I'll tell you the high level things. So step 1 is to show that suppose I have something like this. Okay, this is very small. If the mutual information between A, the protocol, and when B equals 0 is now, given B equals 0, A has two options. It's either 0 with probability half or 1 with probability half, right? Because you're in these two cases. Okay. And the protocol is giving you so much information about A that the entropy has dropped from like full to 0.001, right? And you can use this to argue that this implies that pi 0, 0 and pi 1, 0 are very close. So you can use this to say that the distance between what the protocol outputs for 0, 0, and 1, 0 is small. Okay, and it requires some work. We're not going to do it. In particular, the TV distance between these two things is small. Okay, so A has 1 bit of entropy, but pi carries no information about it. If it carries no information about it, in some sense, whether A is 0 or 1, the protocol is not changed. Okay, so that's the intuition. Qualitatively, it makes sense. You just have to quantify it by writing down the definition of entropy, and you can do it. It's not some big thing. Okay, and you can play around with this 0.00 and if it's 0.001, this is something else. Okay, and the same thing will also work from the other side. So similar argument. Shows that is also small. Okay. We did the first one from the perspective of Bob. We do the second one from the perspective of Alice. We get the same inequality again. Okay, we put these two things together and use sorry, it should be 0, 1. So we use these two things together along with triangle inequality to say this is less than or equal to okay. Now, what is this saying? It's saying that the protocols look similar when Alice gets 1 and Bob gets 0, or when Alice gets 0 and Bob gets 1. Okay, they're not, the protocol doesn't look very different in these two input cases. Let me draw a picture. So I have 0, 1, okay? They run the protocol and they get some transcript, which is a random variable, right? Because the protocol could be using randomness, okay? And then the same way, if they get 1 and 0, they run another protocol. I mean, the same protocol, but the transcript is 1, 0. Okay. And what we deduce so far is that the first, like black one, is close statistically to the green one. All right. And here's where there's some very nice property of distributions and protocols. It's called the cut paste inequality. Okay. Again, we are not going to prove it because of time. So what is a cut paste inequality? So think of what the protocol does. From Alice's perspective, these two are looking the same. Right? Bob doesn't know whether Alice is 0 or 1, except from what Bob sees on the protocol. So just go to the very extreme and say these two are identical, exactly identical. Right? Pi 0, 1 equals pi 1, 0. They have the same exact distribution. That would mean that Bob is not able to tell whether it's 0 or 1. And same for Alice. Okay. So in particular, you can show that if okay. So this is called cut paste inequality because it's saying somehow if the protocol looks the same whether I have 0 or 1 and whether you have 1 and 0 for me, then it should be the same whether it's 0, 0 or 1, 1 as well. If 0, 1 and 1, 0 are same, then all four sort of combinations should be the same. Because the only thing that we see is from the transcript. Okay, from your perspective, whether I have 0 or 1, what I'm saying looks the same, then it should be the same whether whatever combination I use. Yeah. Sorry, say that again. Oh, here. Yeah, that's the statistical distance. So basically, there are various ways to make this calculation exactly precise, but basically think of it as a way to measure the distance between distributions. So that's why it's a sketch. I didn't want to go into these calculations for the 1-bit case, but yeah, so this is like the statistical distance. Yeah. Same as 1, 1. Yeah. One norm is basically the one norm. Exactly. Is the one norm of the probability distribution after the subtraction. But the point is that you have this magical cut paste property, right? This is true for protocols. If what I say for 0 looks the same to you as when I say 1, then all 4 should be the same. Okay. And the final contradiction is that you cannot have this because the output should be different. NAND of 0, 0 is 1, NAND of 1, 1 is 0. Okay, so that's where the contradiction comes in. Contradiction because okay. So I have two inputs where the final output is actually different. And I'm supposed to be doing that from the protocol itself. So the protocols are exactly identical. How can you have this? And you can also get a quantitative version. Right? The statistical distance between 0, 0 and 1, 1 is at least 1 minus 2 times the success probability. 1 minus 2 times the 0.9, 0.1, so it's like at least 0.8. Okay. So let me stop here. I agree that I did skip this last part, but it's a little bit tedious to do these calculations with the entropy and so on. So that's why I only presented the qualitative way of doing the 1-bit argument. Okay. But the real deal is in the protocol, the cleverness of the protocol, and how you get the averaging out of it very nicely. Okay. All right. So let me stop with that, and I'll see you on Wednesday.